Hi, my name is Ueda from Georgia Tech. The other speaker is Michael LiBretto. The work we present today is essentially from Mike's PhD dissertation. The title of the talk is Posture-Dependent Robust Stabilization of Flexible Base Robots. I will go ahead and give a high-level overview of the project first, and then Mike will take over. We are interested in robust control of a manipulator on a flexible base. The base of the link mechanism is not always rigid in many manipulator systems, such as mobile manipulators, machine tools, and humanoid robots. We want to apply task space control of the end effector for precise positioning to a flexible base robot. Again, the flexibility of the base comes from the mechanical compliance. If the base is also controlled, its servo stiffness can also be a source of flexibility. Even if the manipulator itself is rigid, dynamic coupling between the rigid arm and base makes the system difficult to control due to the flexibility. I also want to mention that flexibility is difficult to measure or model in general due to a lack of high-fidelity model or simply sensors, making model-based or sensor-based approach practically impossible. To perform task space or Cartesian space control, we can use a sensor such as vision or IMU to form a closed-loop system. Note that manipulator systems, including humanoids, are redundant, meaning that multiple kinematic solutions achieve the positioning of the endpoint. Here, the question is, how can we optimally choose a posture so that we can stabilize the feedback system? The goal of study is to stabilize the feedback system by using as simple control as possible, such as task space feedback. In other words, is it allowed to neglect complex flexible base dynamics and form a closed-loop system, simply assuming that the system is completely rigid? It is not usually the case, because the flexible base robot is not a collocated system. Our approach is to evaluate the posture-dependent robust stability of a linearized model about endpoint. We specifically use the margin proposed by McFarlane and Grover that identifies all stabilizing controllers. Regarding the arm postures, we expand the concept of robust arm configuration to determine the optimal posture. Unlike many other numerical applications of H-infinity robust optimal control design, we present an analytical expression of the stability margin for a rigid body system and consider flexibility as a fluctuation. We just want to give a quick review of a well-known concept about actuator sensor collocation, which is related to the positive realness of a LTI system. If we put the sensor and actuator on the same body, the system is called collocated and known as favorable for closed-loop stability. If collocated, the phase difference between the input and output is within plus minus 90 degrees, also called in phase or minimum phase, which is equivalent to passivity of linear systems. On the other hand, when the sensor and actuator are on different bodies and the flexible element is between them, the situation is called out of phase, and the closed-loop system is most likely becoming unstable as the feedback gain increases. Our interest is extend the concept of actuator sensor collocation to multiple input, multiple output systems. Now the system dynamics is represented in the Modal decomposed form. We first see that the rigid mode is trivially lossless due to a positive definite inertia matrix, which is a well-known property. For the flexible modes, we can achieve a condition on the flexible mode shape, wherein if the coefficient matrix R is symmetric and positive self-definite, so that the mode is passive. This implies that it's possible to select a posture to achieve systemic passivity for all flexible modes. While this metric is useful, its utility is limited by the modal frequencies in the system and in the ability to do total in-phase design.
For the case of MIMO systems, it is very unlikely that all flexible modes are totally in phase. An easy example to look at is this planar manipulator with 3 base flexibilities in x, y, and angular directions. The in-phase property can be evaluated across the workspace for each of its flexible modes. The regions of these plots in yellow are regions in which the mode is in phase, and as you start to consider these modes simultaneously, the likelihood that there will be postures that are totally in phase begins to drop significantly. This problem is navigable if you have modal frequencies that are particularly far apart, which would allow the control designer to avoid excitation of those higher modes, but overall, the selected posture would still not totally be in phase. As an alternative to the passivity index introduced previously, the normalized coprime factor stability margin can be used to describe the stability of the system on a whole. Well known in H-infinity theory, this metric describes the stability of the minimal system described by the normalized coprime factors of the open loop plant P, as well as the system's robustness to modeling errors. At its center, the NCF stability margin requires the computation of the Hankel norm of the concatenated matrix n tilde m tilde. Or equivalently, one can use the quantity on the right, which is dependent on the solution of the generalized filtering and generalized controller algebraic Riccati equations. The solution of Riccati equations is generally done numerically, and even then, solutions are not always guaranteed. But because we're working with systems that are balanced and minimal, we're guaranteed a solution, and moreover, the stabilizing solution is guaranteed to be symmetric positive definite. The biggest question raised by all of this is how we can make definitive claims about any of these systems. For that, we would obviously need some analytical solutions so that we can make proofs one way or another. This is generally not possible, but for the class of all rigid or double-integrator systems, we have solved both the GCARE and the GFARE to find a definitive solution for the normalized coprime factor stability margin. As one last preliminary, it is necessary to realize the modally decomposed transfer function into a state space system. For a purely rigid system, however, we can truncate the necessary parts of the AM, BM, and CM matrices, taking care to leave the system general through using a map, which we call F, to change the distribution of the rigid mode between the input and output sides of the state space system. As a motivating example, we can see the NCF stability margin applied to an SISO system and a planar 2R manipulator. In each of these, larger values indicate a more stable system, and in the case of MIMO systems, we can evaluate this metric at every point in the system's workspace. Looking at the SISO system on the left, we see a clear division in the stability margin between non-collocated and collocated systems, and this boundary occurs when the system is purely rigid. This value very clearly occurs at the intersection of the above curves and seems to be constant for all values of the rigid mode. This is evidenced by the evaluation of the NCF stability margin for myriad rigid systems in MATLAB and can be done using the NCF syn command. Overall, this sets a very clear performance indicator as to whether or not a multimodal system performs better or worse than its rigid subsystem. In evaluating both the GCARE and GFARE for a rigid body system, we find that the characteristic equation is equal to lambda squared minus 6 lambda plus 1 quantity raised to the n. This means that the polynomial itself is constant with roots of multiplicity equal to the number of rigid body modes in the system. When evaluated, the maximum root of the characteristic equation yields a constant value of 1 divided by the square root of quantity 4 plus 2 root 2, which is equivalent to the value found in the MATLAB demonstration. The important result here is that this value is constant and is shared by every double-integrator system regardless of dimensionality or redundancy. Should the manipulator be redundant, special care must be taken in the map between the task and joint space. However, this will not impact this solution. We arrived at this result through the simultaneous evaluation of the set of matrix quadratic equations resulting from the blockwise expansion of the GCARE and GFARE. This solution was possible because we leveraged the positive definiteness of the rigid mode to find matrix square roots in the solution of both x2 and z2 first, then followed the rest of the algebra through. Notably, the solutions of z and x are functions of only the rigid mode and its distribution factor f, and have a reciprocal structure of sorts. Each of the rigid body quantities in the elements of z and x are inverses of one another, and this would even be the case if there was an unequal distribution of the rigid mode throughout the input and output. When the product Zx is found and its characteristic equation is evaluated, the rigid mode terms and the off-diagonal terms cancel to identity. This results in the aforementioned constant characteristic equation despite the matrix being a function of the rigid mode. After analyzing a purely rigid case, the natural extension is to see what happens upon the inclusion of a flexible mode. We know from our work with the modal passivity analysis that for a flexible mode to be passive, it must be symmetric positive semi-definite in rank 1. Using this, one can vary the flexible mode so that it remains passive by assigning it the structure shown on right. In varying this residual and scaling the rigid mode in this way, the NCF stability margin for a variety of in-phase systems can be analyzed simultaneously. It is clear from this graphic that these in-phase flexible systems have stability margins greater than or equal to that of the rigid system, indicating superior performance. Interestingly, however, two distinct fixed points occur in the plots regardless of this scaling. It is for these flexible modes that we can simultaneously diagonalize all modes in the system. The invariance of these points with respect to the scaling of the rigid mode instructs us that these fixed points are related to the mode's invariant subspace. Taking a step back and looking at the intuition surrounding the flexible mode as an algebraic structure, when you consider it to be a linear transformation from the input space, whether that is torque or velocity, to the task space, it is easy to see that they always project all inputs onto the span of the same line in the plane when d equals 2 or space when d equals 3. This line is defined by the generating vector for the passive flexible mode, 1 beta. While an alpha was used in the preceding analysis, we are more worried about the span of the vector here, so the alpha may be omitted. When the generating vector lies along any of the principal axes of the rigid mode, that would be the vectors comprising its eigenbasis E, we can diagonalize the flexible mode so that it takes the form of the similarity transformation of a scalar times a selection matrix P. Substituting this relationship into the transfer function representation of the flexible-based system, the expressions for each of the modes can be expanded and the basis can be factored out. After the change of basis, the system can be recognized as G', which is diagonal in the invariant subspace of the rigid mode, and all of the subsystems on its diagonal are SISO. This indicates that within this eigenspace, the actions of either axis are decoupled, and the subsystems can be analyzed independently. This diagonalization is analogous to converting the robot in question into a Cartesian robot. Each of the axes can move independently and act without inducing motion in the other for both rigid body motion as well as any induced oscillation. It is for this reason that we can say that the overall system is only as stable as its least stable part. So how can we show that? If we realize the transfer function G' as block diagonal matrices of conformal size and evaluate the GCARE and GFARE, we find that they have block diagonal solutions because of the decoupled subsystem dynamics. Therefore, the resulting characteristic equation is the product of the characteristic polynomials of each of the subsystems in the aggregate. It is for this reason that the NCF stability margin becomes that of the subsystem with the largest root and therefore the lowest stability margin. While this is good for analysis, it is an overwhelmingly special case. Should the basis through which the modes are diagonalized be not orthogonal, there will not necessarily be decoupling and this solution may not hold. Returning to the earlier motivating example, we can see this in action. Here we have a system with an in-phase flexible mode and a rigid mode. When we take the eigenvectors of the rigid mode and put them into the same form as our generating vector, which is 1 beta, we get two possible generating vectors that will force the flexible mode to project onto the principal axes of the rigid mode. At either of these values of beta, 4.0258 or negative 0.2484, we see that the NCF stability margin is that of the rigid mode, which is notably less than that of an in-phase flexible mode, meaning that the NCF stability margin took the form of the less stable subsystem. This material was included in previous work published in ASME Letters in Dynamic Systems and Control. There we used the NCF stability margin to select postures of high robustness that will result in low magnitudes of induced base oscillation for a remote planar manipulator with 3 degrees of flexibility in its base and a planar redundancy from a mobile undercarriage. As stated previously, the NCF stability margin can be applied to the workspace of a manipulator. A contour plot on the left shows just that. The two postures are called out with data shown on the table in center, and the plots on the right indicate regions that are approximately passive for the 3 flexible modes in the system. The leftmost posture, posture A, where the manipulator arm is folded up, is said to be less robust than the outstretched posture, posture B. This is intuitive because it is closer to the regions of passivity for the first 2 flexible modes in the system. When given a position regulation task for each of the postures A and B, the posture of higher robustness demonstrated lower magnitudes of induced base oscillation compared to the posture of lower robustness when using the same feedback controller. This supports the use of the NCF stability margin to select postures that have a higher overall stability. As a result of this work, the value of the NCF stability margin for rigid systems was proved to be constant across all double-integrator systems, and the concept of simultaneous diagonalization of modes was proven. Overall, this provides a numerical performance target when discussing systems with flexible modes. Thank you for your time.